In this particular lecture, we are going to discuss mixing and blending. Let us first try to understand what is the purpose of mixing or blending. What does mixing means, what does blending means, and what are the purposes of mixing and blending. Okay. So, there exists wide variability in the characteristics of cotton fibers within a bale and between bales also. That is, the different characteristics basically means fineness of the fiber or strength or short fiber percentage, color, trace percentage, maturity. These are different parameters which defines quality of a cotton fiber. These parameters, they vary within a bale and also between bales. These characteristics vary because of many reasons. Even within a single seed, the fibers that we will get, they will be of different length. There will be long fiber, there will be short fibers. So, they not only vary between bale or within bale, they even vary in a particular seed as well. Otherwise, they also vary depending upon the growth area, that is the country or the region, depend upon the climate where the cotton is grown. There could be seasonal changes, and there could be differences because of genetic nature of the cotton. So, there are many reasons why they vary. As an example, we will give you here the range of fineness variation in a cotton bale. Like within a bale, the fineness can vary from 0.25 microgram per inch to 0.5 microgram per inch. Similarly, between bales also it can vary, as shown here. It could be 1.5, 2.25, in this range it can stay. So, this range of variation is stated in this particular slide. So, that could be the typical range of variation within a bale and between bale. Now, if this variation is there, and therefore, what we can expect that the yarn that we produce out of this will also vary in its properties, which is unwanted. What we need is to produce a yarn whose properties are consistent along the entire length of the yarn that we produce. Therefore, mixing of cotton from different bales averages out the variation within and between bales. That is the purpose of mixing, so that we can produce consistent quality yarn. Otherwise, the yarn property will vary from place to place. Now, blending is also means basically mixing, but this term blending is used when you mix fibers different in chemical nature. As when you mix cotton with cotton, then we say it is a mixing process. If we mix polyester with polyester, then we call it is a mixing process. It could be viscose with viscose, then it is a mixing process. But if it is cotton and polyester, then we call blending between cotton and polyester. Another example could be cotton and viscose rayon, it is also a blending, or we can have tertiary blend, cotton, polyester, viscose rayon together is also blending. So, you see here the chemical nature of the fiber is changing. It could be acrylic and polyester, it could be wool and acrylic. So, when the chemical nature of the fibers differ and we try to mix them, we call it a blending. Otherwise, blending process and mixing process, they are similar. Now, what are the objectives of mixing and blending? If we try to first learn this, mixing, as we have told already, it is the idea is to average out the variation in the characteristics of fiber present in various bales in a particular bale laydown, so that the yarn properties are consistent or it is uniform. What we produce today and what we produce tomorrow, they should be uniform when we are spinning the yarn from the same set of bales. Sometimes mixing is also done to reduce the production cost. So, there is a sometimes there is an economic reason why do you want to mix fibers coming from different bales. However, one must know the effect of proportion of different components on the processing performance and quality of the final yarn. So, the objectives is, even though the objective is to take care of the cost part, because different bales cost different amount of money and hence sometimes we blend them in order to reduce cost, but we must also know that what could be the consequence of mixing a poor quality fiber, otherwise the quality of the final yarn will suffer. Sometimes if we want to mix a poor quality of fiber, in order to reduce the cost, the processing performance will suffer. There will be too many breaks, there will be too much of wastage. As a result, the spinning efficiency will go down. At the same time, the quality of the yarn also will suffer. The other thing is to produce certain shade by mixing fibers of different colors. This is also done. Sometimes we want to mix black cotton with white cotton or black with blue cotton. That is, sometimes we want to produce a particular shade by mixing different colored fibers. So, in that situation also we have to mix fibers having different colors. The blending part, if we discuss, the main purpose of blending, that is, we are mixing or we are bringing fibers which are different in chemical nature together. It is to engineer the properties in a product for a particular end use. For a given end use, sometimes there are certain properties which are desired, and from a given fiber we may not be able to achieve the targeted properties in the product. Some properties maybe we will be able to achieve, in some properties we may lack, because the raw material is not good enough to achieve those targeted properties. In those situations, we will try to blend two different fibers or three different fibers, because one property, one particular fiber may be deficient in one property, but another fiber is better in that property, and therefore, if we mix these two fibers together, they will be complementing each other, and as a result the final product quality will be much better. Sometimes we also blend to improve the processing performance of a particular fiber by the admixture of carrier fiber. This is also sometimes we do, that in order to improve the processing performance, we add some fibers. Idea is to improve the processing performance. The other thing is to produce certain shade by mixing fibers of different colors. This also we do in blending. So, when it comes to mixing of fibers of different colors, sometimes the colors of the two different fibers which are of having completely different chemical structures, we sometimes mix them. Like let us say we mix white cotton with black polyester, not necessarily that white cotton will be mixed with black cotton only. Sometimes this is also what is done, that the polyester part may be having one color, cotton may be having another color, or viscose rayon may have one color, polyester may be having another color. So, it is also blending, but the idea is to produce a certain shade by mixing fibers of different color. So, these are the differences between mixing and blending as far as the objectives of mixing and blendings are concerned. All right. So, from there we go to the next slide now. Now, whenever we want to mix the fibers together, we would love to know what are the mean characteristics of the mix. So, how to calculate certain the average values of certain fiber parameters. Let us say we want to mix n fibers components together and they are weighing W1, W2, W3 up to Wn. Okay. So, the total weight of the fibers in the mix will be sigma Wi. This is very easy. Let us say Pi is the individual mass contribution, the fraction of fiber components are also can be found out. So, P1 will be W1 by capital W, P2 will be W2 by capital W, like that we can Pi will be Wi by capital W. So, these will be the mass weight proportion of fibers, and therefore, the average length of fiber in the mix is going to be, if the average length is Lm, it is going to be sigma Pi Li, or Li the mean length of the component I. Okay. This is how this simple formula can be used to find out the average length of the fibers in the mix. Similarly, we can find out what is the average strength of the fibers in the mix. So, that is going to be sigma Pi Si, where Si indicates the mean strength of the component of the ith component. So, this way we can find out what is going to be the average length of fiber in the mix or average strength of fiber in the mix. The other thing which will be of some interest to us is what is the average diameter of fibers. Similarly, we can say suppose D1, D2, D3 are the diameters of the fibers and there are n components, and P1, P2, P3 are their respective proportions. Therefore, let us say dm is the average diameter of the mixture. Okay. So, fractional contribution in the cross sectional area of each component we have to first find out, and these values are as given here. Pi d1 square by 4 is the cross sectional area of the component 1, and if P1 is its proportion in the mix, then its fractional contribution to the average cross sectional area of the fiber is going to be P1 pi d1 square by 4, for the second component is going to be P2 pi d2 square by 4, and like that P3, and it can go up to Pn. All right. And the cross sectional area based on average diameter is pi d square m by 4. So, now what we can write is that pi dm square by 4 is equal to P1 pi d1 square by 4, P2 pi d2 square by 4. It will go on up to Pn pi dn square by 4, that is sigma Pi pi di square by 4, and we sum them up from 1 to n, where n is the number of components, and this will give me a value what, which will be pi by 4 being constant, we can take it out. So, within sigma which is coming Pi di square, I varying from 1 to n, and from there therefore, what is dm square? is, because pi by 4 and pi by 4 will cancel, therefore, d m square is sigma p I d I square. This becomes the relationship between the average cross sectional or average diameter of the fiber and the individual diameter of the fibers. And if we remove squares, then we get dm equal to root over sigma p I d I square. So, this relationship will help us to find out what is the average diameter of fiber. From there, another thing will be interested sometimes to know what is the mean fineness of fiber. So, average fineness cannot be a simple arithmetic average, since number of fibers of a given blend component will depend upon its own fineness and weight. This is very important to remember or know, that we cannot find out the average fineness by simply finding out the average value of the fineness of the component. It is not by simple average, because depending upon the weight and the fineness of individual component, this will decide how many fibers are there of a given component. So, it should be based on the total weight divided by the total length. Fineness by definition is weight per unit length. So, we have to find out what is the total weight and what is the total length of fibers. Let us say W is the weight of bales of individual blend components, and M is the microneedle reading of individual blend components, and P is the percentage by weight of individual blend components. And therefore, what is going to be the mean fineness? It is going to be total weight of fibers divided by total length. So, total weight of fiber divided by total length. So, we have to find out what is the average fineness. So, average fineness will be total weight of fibers divided by the total length in the mix. So, total weight of fiber is going to be W1 plus W2 up to Wn, if these are the weight of individual components, and the total length will be the ratio of weight by micron value, which is microgram per inch. Therefore, W1 by M1, W2 by M2, Wn by Mn is going to be the sum of these is going to be the total length, and hence if the relationship is like this, then the dividing by the total weight, if I divide it by the total weight on the right hand side, both the numerator and denominator, then what we get? W1 by capital W, W2 by capital W up to Wn by capital W. Similarly, the denominator is also divided by capital W. So, there is no change in the value, we divide both numerator and denominator by the sum of the weight of all the fibers, and now the numerator becomes P1, W1 by W becomes P1, W2 by capital W becomes P2. So, the numerator becomes sigma Pi and the denominator becomes sigma Pi by Mi, and hence Mx bar will be sigma Pi is going to be 100, because P indicates here the percentage by weight of fibers. So, sigma Pi is going to be 100, therefore, Mx bar is going to be 100 by sigma Pi by Mi. This is going to be the formula by which we can find out what is Mx bar. Now, we go to mixing and blending form and stages. Now, in the spinning line, the mixing can be done in different stages or at different stages and in different form of the fibers. So, in the beginning it is bale form. So, we take the fiber in the bale form, the stage is blow room, and the machine through which we can mix the fibers taken directly from the bale is by automatic bale opening machine. We will discuss about them. The next one is the flock and tuft form, which is within the blow room line. It could be hand stack blending, automatic blending equipment, or by the help of multi mixtures. We could also blend in the lap form, which is also within blow room, and the machine which is used is scratcher. We can mix the fibers in the sliver form, that is done in the machines called draw frame or sliver lab machines or Kumba draw box. There are quite a few places where we can also mix the fibers in the form of a sliver, which you learn what a sliver is later on as you go through the entire course. It could be wave form, pre-combing stage, blending draw frame, Raven lab machines or blending draw frames which are available. There also we can mix the fibers in the form of a thin wave. Also fibers can be made in the form of a roving at the spinning stage, that is the last final machine, a ring spinning machine. We can feed rovings from two different fibers. We can put them together and process them together and make a yarn. That is also possible. But in this particular lecture, we are going to discuss 1 and 2, as how do we mix them in the blow room at the beginning or within the blow room line. So, this is what we will be discussing. Now, mixing techniques, if we discuss in general how we can mix the cotton tuft. See, you must have learnt how to mix sugar and sand, how to mix two liquids, how to mix two solids. So, there are different types of mixing techniques which are used when you want to mix two liquid or when you want to mix two solids which are in the form of granules, like as I said an example sugar and sand. But when we think of mixing fibers, then it is a little different, because though fiber is a solid, but is not like granules. Fibers are very soft and very fragile, and they have mostly they have a length dimensions. They are too thin, and therefore, the way we want to mix them has to be totally different than the way we mix either liquid or granules. They cannot be same, because if we follow a similar technique as it is used for small particles or for liquid, our fibers will be they will all get entangled, and maybe they will also break. Entanglement will be too much, and therefore we will not be able to really process the fibers at all. So, we have to develop a different technique to mix the fibers together. So, method 1 is shown here. How it is done? One process is develop a stack of cotton tufts in the form of layers after layer, like we are showing here in the diagram. There is a stack 1, 2, 3, 4. 4 different colors are are given here just to show it is a stack having in the form of layers. So, we have to each layer is representing suppose a particular variety. So, here like yellow color represents one particular variety of cotton, green is another variety, white is another variety. So, we form stacks of cotton and put them in the form of layers one on the top of the other, and now we remove these tufts by cutting either vertical or slant slices. Like in this case we have shown here as these lines, vertical lines in the lower diagram shows that along this if we cut it and take it out as shown as a slice, then this particular slice is having cotton from 4 different layers, and if this part is fed into the main processing line, then this yellow, green, white and the gray color cottons will get mixed. So, this is the type of process which we follow in order to mix cotton of different varieties. That is, we form layers and then first we produce horizontal layers. We will show it how it is done, but this is one principle which is or the technique or the method whatever you say which is followed. So, therefore, each vertical slice will consist cotton tufts originating from different bales and thereafter they get mixed because they are fed to the main line. The other thing is method 2 is that instead of horizontal layers we can have vertical layers or vertical column of cotton tuft, that also we can produce like shown it here, that same thing, but this is now vertical. Here also each column will represent cotton produced over a certain time period maybe or cotton tufts produced over a certain time period, like we are filling, or you can imagine that there is one vertical column represents one particular variety of cotton. Let us if that is possible, then we can, that is yellow, that is grain, and so these are cotton of different varieties. If we can think vertical columns representing different varieties of cotton, and now we cut slices from the bottom as shown here and feed it to the main line. So, the very first slice will be having material coming different columns and they will all get mixed and they will be processed together. So, there will be possibilities of mixing. So, the colors may represent cotton coming from different varieties or tufts belonging to different varieties of cotton, or it can also represent that tufts being fed to these columns one after the other. So, that as soon as we remove cotton from the bottom, the tufts fed at the very first column gets an opportunity to be mixed with the tuft fed the second, third, fourth, fifth, sixth, seventh, eighth column. That means, tufts which are fed at different point of time, now they get an opportunity to be mixed. So, this is how we try to mix cotton in the form of tufts only, and we maintain this tuft form. Okay. Now, hand stack, now the actual blending process, first of all hand tack or sandwich mixing or bean blending, whatever we say, there is a which is normally done manually. So, what you do? You show here there is a rectangular box, here the bale of cotton is fall open manually by hand and sprayed over a large closed area in the form of layer of thickness 15 centimeter roughly. This is the old practice. You see each layer, layer 1, layer 2, layer 3 form 30-40 layers, one on the top of the others. So, this process is entirely done manually. Directly from the bales we remove the fibers in the form of big chunks and spread it out on a floor. So, then we take cotton from the another bale and also spread it on the top of the first layer. So, one after the other we keep on forming layers, and these layers are being formed in such a way that the cotton which represents each layer, they are coming from different bales. And in a sandwich fashion we are basically making or producing layers after layers. After this, the stack is allowed to stand for 12 to 24 hours for aerate and conditioning. Then you leave it for conditioning. You will find that unless the cotton is conditioned, their processability suffers, and therefore, you allow it the stack to remain as it is for almost 12 to 24 hours. But the material is now emptied vertically. You see we are again cutting like slice 1, 2, 3, 4 like this, and sideway we cut it and then we feed it to the main line. So, form layers vertically one after the other, but cut the layers vertically, but the layers where you are forming layers one after the other in the form of sandwich fashion, and then remove them sideway, cutting vertical slices. Now, this is what is done manually. We can do the same thing with the help of a proper machine. So, machines are now available, like one of the machine, their sketch is shown here on the right hand side, and this 1, 2, 3, 4, 5, 6 which you see, these are basically chambers within which we place our cotton. Now, look at this machine. If you look at the design feature of the machines, it consists of 6 to 10 vertical compartments or chambers. So, in this case we are showing 6. At the bottom there are some take up rollers as shown here. First, air current will carry the cotton tops and deposit on a condenser which traverses across the machine and drops tops. So, the cotton is coming from here, the condenser is as shown here. So, tufts are depositing on the surface of the condenser cage, and then they are brought down, and this entire feeding unit we can say keeps on traversing back and forth, so that the material, these tufts are dropped into different compartments. So, compartments are filled up to a certain height. This height can be adjustable. For that we have sensors, and from the bottom the cotton tufts are taken out with the help of take up roller, and these tufts are then passed on to the conveyor. Conveyor is resting just below the take up rollers. So, this conveyor is taking the cotton tufts which are coming from all 6 compartments, but what we can say that means in a way we are producing vertical columns of material one after the other, and from the bottom we are taking them out. So, material fed to different columns at different times, at different compartments at different times are actually getting mixed when they are coming together on the conveyor, and the conveyor is taking them forward and feeding it to the main processing line. Typical filling height could be 6 meter. The length of this compartment could be 1.97 meter, width is 0.6 meter, volume is 7.35 meter cube, capacity could be 20.4 kg, and the density of the cotton tuft could be 0.29 kg per meter cube. Now, that is the typical design of a multi-mixture. The way the multi-mixture operates, there are two ways. One is to fill the compartment completely and then emptying it as in stack mixing, or to run the mixture continuously. That means, this is discontinuous way of operation, and or it can be run in a continuous mode. And discontinuous mode of operation, if we discuss it here in details, see on the right hand side you see a diagram, the compartments from 1 to 6 are there, and the compartments are filled from bottom to top, and then when all the compartments gets filled up, then only the machine, the condenser will stop feeding. Now, let us consider each vertical column being divided into 6 boxes. You see that we have drawn parallel lines, horizontal lines, and each compartment there are 6 boxes, 1, 2, 3, 4, 5, 6. So, there are 6 boxes. Therefore, this entire mixture consists of now 6 into 6, that is 36 boxes. So, each compartment divided into 6 parts, and therefore, total number of box that gets formed due to this will be 36. Now, the numbers which I have put it here, this number indicates the filling time of each box. So, on the first column at the bottom, the value is 3. That means, this particular box takes 3 minutes to get filled up. Then the next box, it takes another 3 minutes. So, 6, then 9, then 12, then 15, then 18, like that. The time to fill up different boxes are shown here. So, it starts the very first box at 3 minutes is completion time, the last box the value is 108. Now, if I look at the when the material moves out from this machine, then what we see here, that the bottom layer which will move out by this, because of this delivery rollers, this layer was formed, or this layer is formed by the tufts which are fed at different times. So, feeding time of these tufts in the bottom layer are how what 3, 21, 39, 57, 75 and 93. These are the time when this bottom layer was filled up. So, when this layer moves out, what we can say is that the material which are fed to this machine at different point of time, they get an opportunity to be mixed up. Similarly, when you go to the next layer, you see the next layer, when the second layer, this is the first layer which moves out, then this is the second layer moves out. In this particular layer, the boxes are filled up at time 6 minutes, 24, 42, 60, 78 and 96 minutes. And therefore, the material, the layer consists of material which are fed at different point of time, and hence the material has a chance to get mixed up. So, what otherwise this opportunity is coming because the sequential way in which we are feeding the tufts into different chambers, and then we are taking the tufts out from the bottom. So, we fill up the chambers and take them out in other directions. So, this helps us to mix tufts which are flowing through the machine in a continuous manner to get mixed up. Otherwise, the mixing efficiency will not be good, or if I do not have a machine like this, then whatever mixture we have produced at the beginning, that mixture will keep flowing through all the machines and they will never have an opportunity to be mixed. We will discuss these things more, in more details as we go through this course. So, from discontinuous we go now. Another important thing is the concept called blending delay time. What is this? The largest filling time difference of the tufts which are getting mixed together is the blending delay time. Now, if I go by this diagram, then you see that the tufts which are fed at the first 3 minutes getting mixed up with the tufts which are fed at 93 minutes. Therefore, the blending delay is 93 minus 3, that is 90 minutes. We say that this is the blending delay. So, the tufts which are fed at 3rd minute has an opportunity to get mixed up with the tufts which are fed at 93 minutes, and the larger this value, more the blending delay, the better it is. In the continuous mode of operation, it is a little different. You see here the similar picture is shown here, but now the feeding style is different. What I see here, that these chambers are not filled from bottom to top. The first chamber is filled to 1/6 height, the second chamber to 2/6, third is 3/6, like that. So, if we look at the heights, it has a step pattern, a staggering pattern. The last chamber is filled to its fullest height. So, this is how first we fill up all the compartments or all the chambers one after the other. The filling time of the box is also shown by this number, as we have now written in the previous case. In this case, when by the time we fill up the last chamber, you see there is a part of the machine remain empty. So, the unused capacity is how much? Number of boxes empty divided by total number of boxes that we have in this particular machine. So, this will give you a value 42%. That means 42% of the capacity will not be used in this case. But now, if we go how the operation starts, as the compartment gets filled up, the feeder moves to the first compartment, that is after filling up all from 1st to 6th, the feeder will go back from 6th to first compartment again. Now, once it goes there, now the machine is ready for operation. So, we have to wait till we fill up these compartments in this particular fashion, and by the time the feeding unit goes back again near the top of the first chamber, now the machine is switched on, that is, now the delivery starts. What happens now? Delivery starts. So, the very first layer at the bottom gradually moves out depending upon the delivery rate, but the way the machine is set, that the rate of fusing is so adjusted that the time required to empty the first layer equals to the time required to fill the compartment, one single compartment, plus moving time of the feeder to the next. After filling it, the feeder has to go from compartment 1 to compartment 2, then it will start filling up compartment 2, then it will go from compartment 2 to compartment 3. Like that, it has to move from one compartment to the other compartment. But when it goes to 6th, then it has to travel a long distance, because it has to come back to 1 again. Now, this way the machine is going to work. The material belonging to very first layer which get mixed up were fed at what times? If you look at the timing, 3, 6, 12, 21, 33, 48. These are the times where when the material was filled up, when these boxes all filled up, or the material was dumped into this. So, the actual blending delay in this case is going to be how much? 48 minus 3, that is 45 minutes. So, this is the time difference, as you have said earlier by definition, what is blending delay. So, the blending delay time for the very first cycle, when the very first layer is moving out, is 45 minutes. Now, as the layer moves out, the material fed at 9, 15, 24, 36. Now, this layer now comes at the bottom. So, now if you look at the timings when this boxes are filled up, 9, 15, 24, 36, 51, but the box at the bottom of the very first column, it was filled up at 66 minute, because after 63 it goes back here and then start filling. By the time this bottom layer moves out, the entire compartment also gets filled up, gradually getting filled up. So, you can say that this box, very first box at the bottom, was filled up at the 66th minute, and therefore, the blending delay time is going to be now 66 minus 9, the earliest and the latest time difference, and that is going to be 66 minus 9 basically means 57 minutes. Okay. So, now this is 57 minutes for the second layer. So, what we see that for the first layer the value was 45, but for the second layer it moves out, the value is 57. So, that means the BDT will keep on changing, and how long it will change? When the fifth layer will move out, then the machine will come into equilibrium in terms of its operations. So, the BDT will keep increasing and settle when the fifth layer will move out from the mixture, or we can say at the fifth cycle. So, for another cycle we are showing it here. For the third cycle, the value is shown here, it will be 84 minus 18, that is 66, and for the fourth cycle it is going to be 102 minus 30, that is 72 minutes. Fourth cycle, or for the fifth cycle you can calculate how much would be the value. So, this way the blending delay time gradually is rising starting from 45 to till now 72, and you can calculate for the 5th cycle also, and it will then stabilize. It will be going like this and stabilize. So, it is a layer or cycle 1, if I say 1 has a value 45. So, we will start from value, we will start like this. Just a minute. Let me do it again. So, plot like this. This is the cycle. Or feeding cycle, and this is blending delay time. It will go like this, the minimum for this very first cycle, then second, then third, fourth, like that it will go, and it will stabilize when at the very 5th cycle it will stabilize. This is how the blending delay time will change initially, but then it will be fixed, then onward it will not change. This is how, and the operation will be continuous in nature. So, in this case the operation is continuous in nature, but in the previous case we fill up the entire chambers or entire multimixtures, and then we stop feeding and we allow the material to move out from the mixture. When the entire mixture becomes empty, we start feeding it again. So, that is a kind of discontinuous process. However, this is a continuous process. Now, sometimes we can also use the machines in two ways. We can have a mixing equipment in tandem can be used, where we can have a parallel processing situation or a series processing sequence. What these two means? Parallel processing, we can have two multi-mixture as shown in the diagram, mixture 1 and mixture 2. So, in the line we can have two mixture placed side by side. The tufts detached by the bale opener are fed successively in the multi-mixtures. In parallel process, individual mixtures has an additive effect of doubling. If the number of compartments are x and y in the two mixtures, then the doubling factor is going to be x plus y. In this case is going to be x plus y. They are working parallelly. That is, four-fold mixture in parallel will have a doubling factor 4 plus 4, that is 8. That is, it will be equivalent to basically a mixture having 8 compartments. In a way, that is what it basically means. That is, if I keep two mixtures side by side, allow the tubs to go to both the mixtures, the output goes again to one common conveyor. Then is basically it is equivalent to a single mixture with 8 compartments. Series processing. The series processing, there are two mixtures, one behind the other, that is what is series processing. So, tufts detached by the bale opener are fed in the multi hopper mixture or multi mixtures, whatever name we can say it. In a series process, individual mixtures have a multiplicative effect on the doubling. If the number of hoppers or compartments are x and y in the two mixtures as shown here, then the doubling factor is going to be x into y, not x plus y. That is the advantage we get. Therefore, if we have both of them have 4 compartments, the doubling factor is going to be 4 into 4, that is 16. So, you see here the mixed material from the mixture 1 is going to mixture 2, and therefore, when the material moves out of mixture 2, there is a very intimate mix that we can produce, intimate mix of the tufts that we can produce. So, it is always advisable to use the mixtures in series than to use them in parallel. So, if we plot compoundment versus doubling factors, then for parallel processing we get a straight line as shown here. So, if we have 8 compartments of 2 machines, the total doubling factor is going to be 8 plus 8 16, but if we have 8 compartments 2 machines working in series, then we have a doubling factor of 64. So, there is a great advantage in using the machines in series than to use them parallelly. Okay. Now, we will discuss another machine, and this machine, the name is very popular machines, it is known as Unimix, is also a kind of multi-mixtures. Now, this machine, if we look at this machine design feature of the machine, it consists of a mixing unit and a cleaner in tandem, that is there is a mixing unit and there is a cleaning unit. These two can work together, or we can remove the cleaning unit and allow the mixture to work on its own. And the mixing unit consists of 3 sections: storage section, condensing section and delivery section. So, you see the storage section, the condensing section and the delivery section. These are 3 sections of the mixing unit. There are 8 vertical compartments with partition wall. The compartments are shown here 1, 2, 3, 4, 5, 6, 7, 8. A lattice of the conveyor is there at the bottom. Also, we can see the lattice. Lattice brings material stacked near inclined spike lattice. The spike lattice also see, as we have seen in the case of hopper feeder or hopper belt breaker. You have a Hübner roller, we have a stripper roller. So, this part looks like a hopper bell opener or hopper feeder, exactly similar in terms of constructions. And there is a vertical chute which is the delivery from this machine, and from the vertical chute the material from the delivery chute can either be transported by suction to the next machine, or it can be fed with a pair of roller to a opener or to a cleaning unit as shown here, and the output of that unit then can be fed to the next machine. So, this is how the Unimix is going to look like. So, there are compartments, and but what we see here that the compartments are vertical, but from the bottom they take a right turn. So, the path of the material in each compartment, the path from the top of the compartment, or you can say from the bottom of the compartment to the spike lattice, this path is different for different compartment. So, the material has to travel different distances. The material from compartment 1 will travel a short distance, the material from compartment 8 has to travel a long distance. So, here also we are showing the material in the form of layers, subtle layer. So, different layers have got different colors. So, we are showing the material that the colors are different, and you see there are 8 layers that we are showing it in this case. The flocks or tufts are carried by air and dropped into the vertical compartment first. The column of tufts move vertically downward and then takes a 90-degree turn to move horizontally. This is what is happening here, the way it has been designed. The 90-degree bend in the material flow produces a shift in the timing and spatial distribution of the transport of fibers from the first to last chute, resulting long term blending. Because see, if we look at here, you will see that the path length being different, the material from the same layer is reaching the spike lattice at different times, and therefore, material belonging to different layers are getting opportunity to be mixed. So, as the material reaches the spike lattice, they are lifted, the stripper roller or part of the material will be returned back by the Ebener roller, the rest goes forward, the stripper roller will remove it as it is, and then it will go into the delivery chute, and from there it goes to an opener or to a cleaner, or sometimes, as I said, it can go directly to the next machine. Now, how the mixing action is happening here, if we describe it, then we can say that, let us imagine that the stack of material within the compartment as layers as shown. I have given the numbers 1, 2, 3, 4, 5, 6, 7, 8. The last layer is the black layer. The path length of the material starting from the top of the compartment to the spike lattice is shortest for the first compartment, but longest for the 8th compartment. The column of material moves at a uniform velocity. The path length from first to 5th layer being same for all. So, from very first to almost 5th, they all move together. So, there is no relative shift between the material which are there in different boxes. You also can imagine them that there are boxes as shown here by these rectangles, and you see they all move together. So, therefore, there is no shift between them till they come to almost 5th layer position. Now, as soon as they reach the 6th layer position, there is a change in relative position. So, here we see here from this layer there is a change, then the white layer there is a change, in the black layer there is more change. So, this change is very prominent for the white and the black layers. So, that means, as soon as the material moves to this 7th or 8th layer locations, there will be a shift between their relative positions. This relative shift of position of material becomes more prominent as the layer will approach the spike lattice. As a result, the material belonging to different layers fade at different time, get mixed up and finally lifted by the spike lattice and fade. So, if we come to the spike lattice, we see that the materials which are ultimately reaching together the spike lattice, these materials are fed to this particular all these chambers at different point of time. So, by this there is a possibility of mixing of the tufts. The other thing is the bale mixing. Though the name is bale mixing, really is not that the bales are mixed together. Bales are very large chunk of material. Each bale may be, as I said, it could be, the weight is quite heavy, 180 kilo or 240 kilo in this range. And the bale mixing, what we do, ultimately mix the material in the tuft form only, but the mixing is initiated at the bale stage. Methodology is that all incoming bales to the warehouse are to be first tested for relevant fiber quality characteristics using HBI or AFIS. You will learn about what is HBI and what is AFIS These are two instruments through which we will be able to test the different parameters of cotton, quality parameters of cotton. Then the bales are divided into different groups, growth area wise or grade wise or some other fiber characteristics wise. They are then classified into different groups. So, divide each group into a number of categories according to fiber characteristics, that is, could be fineness, length and strength or color or short fiber percentage, whatever it is. So, we make them group, and from group to basically subgroup, that is what is done. Now, let us take the case of after dividing them into groups and subgroups, the question that ultimately will come, how do we place those bales in the blow room when the cotton from the bales will be picked up by a machine. So, let us take the case of a bale arrangement where there are only 20 bales in the laydown. Bales to be placed in such a way that bale next to each other are only one category higher or lower than the next bale. This is what we have to remember, that when we place the bales in front of the automatic bale plucker or automatic bale opening machines, two successive bale should be either one category higher or one category lower. That should be the difference. So, if we take, let us say, having a 20 bales, then we can have, if we go for arrangement where we place the bale on both sides of that automatic plucker that works on it, then we have two rows of bales as shown here. So, each row will have 10 bales, and suppose that we have categorized the bales into 5 different categories, 1, 2, 3, 4, 5, depending upon their length only. It is a very simple case. So, we have 5 category bales, 1 means shortest and 5 means longest in terms of their length differences. And because we have to take 20 bales, and depending upon the mixture that we have to produce, let us say we have to take 3 bales of category 1, 4 bales of category 2, 6 bales of category 3, 4 bales of category 4 and 3 bales of category 5. So, this has been already done based upon the average length of the mix that we want. So, that has been decided. So, these numbers are there. Now, what we see here, if we want to have to place them on both sides of the machine, then out of these numbers 3, 4, 6, 4, 3, 2 numbers are odd. Very first one, shortest category bale, we have to take 3, and the longest category bale we have to take 3. So, these two are odd numbers, whereas 4, 6, 4 are even numbers. So, what we can do, that the even number of bales, we already know that category 2 should have 2 bales on upper side and 2 bales on the lower side. Similarly, category 3 we can have 3 each, that we have done it. I will show you, this is also possible. In the lay down 2 we are showing it, that we can take 3 this side and 3 here, and for category 4 we can also have 2 each, because that is even number. For we have a trouble with the shortest and the longest category, because the numbers are odd. So, but there is no way, if we take 1 on the upper side and 2 on the other side, either upper or lower, whatever it is. Similarly, for the 5th longest bale also, we have to take 2 on one side and 1 on the other side, we have no other way. Now, the arrangement could be in the lay down 1, the little difference they have taken for the 3rd category bale, 4 on one side and 2 on the other side, is also in a way is not going to create much problem, is possible. Now, the arrangement is shown here, how the bales are placed, and if we look at this arrangement, what you see here, that if we consider any two bales, then we will find that category wise, category difference wise, they are either one category up or one category down. If we take these two, between them 4 and 5, they are one category up or one category down. If I go here, there is 1 and 2. If I go here, they are same. So, their category difference is 0. So, the category difference 0 is okay or 1, this is acceptable. We are not placing this bale 5th here next to category 1 bale. Then between them the category wise difference is quite large, 1 and 5th. This is what we should avoid. So, we should not place category 5 bale next to category 1 or category 2, because that will have a very large difference in the category. So, the way we have to place the bales, you have to keep in mind that category wise differences is limited to 1 or 0. So, another arrangement has been shown in laydown 2, where also if we try to find it out, we will also see that what I have stated, that you take any, now suppose I take these two, the category difference is 1, here if I take the category difference is 1, we go there, category difference is 1. So, this is how, these are the best way of placing or arranging the bales. Why we do so, we will come to know later on. Or if we want one row of bales, then we can have the way they have been shown here, that we can put the upper row first, followed by the bottom row, and then we have a long one single row or large number of bales. So, instead of 2 rows, we can go to 1 row bale, this is also possible. Now, how the mixing action is happening because of this? Too much difference means, if I suppose I have the category 1 and 5th next to each other, then when the bale placard will come and remove material from the bale category 1 and 5th next to each other, they will get mixed. But these two tufts from category 1 and 5th, there will be large difference in their length, and what will happen, because it will move forward, they will get mixed, and you will have very short and very long fibers always together, and therefore, they may create drafting problems when the material is going to reach the drop frame stage or your speed frame or ring spinning stage. So, to avoid that, we want to make sure that the category difference is not more than 1. The mixing action, in a large laydown, large number of bales are generally lined up. Normally, is not just restricted to 20, we can take 100 bales together. The tuft extractor, that is, which we have on the automatic bale opening machines, the tuft extractor moves or traverses at a constant speed from one end of the laydown to the other. For a 50 meter laydown, the cycle time for one complete traverse is going to be almost 5 minutes. It has to go and then again come back. This tuft extractor keeps removing tufts from the top layer of the bales in a sequence. So, it will go in a sequence, it will start from the beginning and go to the end, and again from the end it will come back on the other side. So, there is a fixed sequence in which the tuft extractor will going to move. The material from all the bales cannot get mixed together at this stage. So, material from the very first bale and the last bale will never get an opportunity to be mixed. Being a continuous process, as the extractor head travels, the plucked out tufts from few bales, maybe 2-3 bales, are mixed at the head itself, and immediately they are passed into the main line for further processing, because there is a continuous flow of material through the machines. So, as the material which is I am plucking first and then releasing them into the main line, it will keep moving forward. So, it will never get an opportunity to be mixed with the material which I am feeding later. So, this is the situation which will arise. So, the amount of mixing at that stage will be limited to only material being plucked from 2-3 bales only. Hence, the tufts from these few bales will be, or where this extract is located, will always get mixed there, but then it will be immediately moving forward. But then if we keep a multi-mixture auto mixture at the later stage, then there only this material will also go, and they will be they will be getting into the multi mixtures in those compartments, and they will have an opportunity now to again get mixed. So, mixing action at the automatic Blake plotting stage is not really much, but some mixing is happening there itself also. Like if we look at this picture, which will make it clear, see, let us say we have one row of bales, and this is the extractor head. It is going from, let us say, from the right hand side towards the left hand side, it is moving. So, when it is extractor head is on the very first bale, first, second, so this is the bale number 1, 2, 3, 4 like that. So, it is here, maybe the tufts being plucked from bale 1, 2, first, second, third will get mixed, and let us say this is the mixture it produces. So, this is the first mix, it moves on, then it plucks material from bale number 4, 5, 6, and this is also produce another mix. So, this is how mix is shown by this circle, and the tufts within them is also shown. This mix are being produced one after the other, first mix, second mix, third mix, like that will reach this stage, where also will produce the last mix. So, so many mixes are produced one after the other, but the delivery simultaneously starting. So, this mix moves forward because the material goes to the main line. So, mix 1, mix 2, mix 3, they will go into the main line one after the other, and therefore, mixture 1 and mixture 3 will not be able to mix together, unless we keep some machines in the line where material belonging to so many mixes can come together, and that job is being done by the multi mixtures. So, multi mixtures has a very, very important role. It can have a capacity of 500 kg material. So, 500 kg of material can stay together in that multi mixture, and therefore, this material has an opportunity to get mixed up at the multi mixture stage. Mixing homogeneity depends upon what is being discussed here. Everybody wants a very homogeneous mixture finally. Use for that what we need to use maximum number of bales in the lay down. The more bales we have, the better mixing homogeneity we will get. The height of all the bales laid should be preferably be the same. Bales should be laid in such a way that no two adjacent bales should have any fiber characteristics differing by more than one step. As I said earlier, the category wise the difference should be limited to 1, or better to remain 0. 0 is not possible, so 1 maximum. The waste should be mixed uniformly. Sometimes we mix waste also. If the waste is mixed with the virgin material, then we have to mix it uniformly for all the 3 shifts. It is not that in one shift you are mixing the waste, another shift we do not mix any waste, that we allow waste to accumulate for the whole day, but they are all used in one particular shift or 2 shifts. This should not be done. Whenever if the company decides to use the waste and it wants to mix it, whatever we collect for the whole day, that waste should be mixed in the next day, right from the beginning of the day to the end of the day, that is beginning of the shift to the end of the last shift. So, that same amount of waste is always mixed and produce small and uniform tufts. So, the tuft extractor or detacher, whatever you use, they should be set to produce smaller tufts. Smaller tufts are better, will be the homogeneity. Shortened ducts and pipes also will help. So, the tuft flow to the ducts also matters from the point of view of homogeneity. So, shortened ducts and pipes are better, and differential waste generated by the component must be taken into account, because different variety of cotton may generate different amount of waste. So, whatever proportion we choose at the beginning, the final stage we may not get that, because one variety may have created more waste than the other variety. So, that information we must have, and accordingly we have to adjust the raw material right at the beginning, so that we get the desired proportion in the output. Now, we discuss the blending. Blending, as I said, that when we try to mix 2 different types of fiber in terms of their chemical nature, let us have fiber A and fiber B. Fiber A is shown by the yellow color and fiber B by the blue color. So, what we do now, tufts are generated from the bells of the 2 components A and B by on a blending feeder, and tufts from the cotton variety A metered amount is fed. From B also some metered amount can be fed depending upon the mixture we want to produce, and then we put them together. Suppose we put them on top of each other, then we have, suppose you want to mix 50-50, then we have for this whole circle 50% will be yellow and 50% will be blue, and when we go for intermingling, then we will get a mixture which will be homogeneous. So, when we mix blue color and yellow color, we get basically a green color. So, if it looks green, that means the mixture is becoming very, very homogeneous. So, that is how we have to go about it. So, metered amount of starch from the 2 components have to be brought together. So, that is how the 2 components are mixed, and then we must have a process of intermingling. So, there has to be a machine where we can intermingle them and create a mixture. So, what we do, what we have, first from the bale we have to create tufts, and for that, and then you have to metered amount of tufts have to be brought together. So, the machine that is used is blending feeder, and blending feeder, that could be volume blending and that could be weight blending. 2 types of blending feeders are there, but weight blending is always better. And what matters here is rate of feed, the density of cotton in the hopper, and the height of stalk within in the case of volume blending. Volume blending means that we take the cotton also the or the 2 materials, which could be cotton and polyesters, and where we have to ensure that the content in terms of volume in the 2 neighboring blending feeders are practically same, and for that what matters is the rate of feed and density of cotton in the hopper or density of the other fiber and this variation and height of the stalk within. These things will also will matter very much, and if they are can be kept constant, then this will work, but more accurate blending is possible when you go for weight blending. So, in the weight blending, the weighing hopper feeders are used, they are much more gives much accurate blend. So, if you look at this machine, the cross-sectional view is shown. So, if we look at this machine, if the machine looks like a bale opening machine. So, we have exactly similar structure, everything is same. What is extra here is basically this part, where we have a weighing pan. That is the only difference. What is you see here, this machine is a Marzoli machine, the company's name is Marzoli, and the structural feature is similar to bale opener. It has extended feed lattice, spike lattice, everything is similar. So, there is no need to repeat it. The extra thing is there is a weighing pan in front of the machine with closing flaps and bottom flaps. Here that is there. And so, what we do here, this construction and this the way of this works is, we have already discussed the way a typical your bale opening machine works, exactly construction wise is same. So, the same way it is going to work again. The extra thing which is here is the weighing pan. So, weighing pan, what do you do with the help of weighing pan? Generally we have 4 blending feeders, you see it here one after the other, 1, 2, 3, 4. There is a conveyor which runs perpendicular to the blending feeders. So, during normal operation, a set of blenders 3 to 4 work together. Each blender runs one type of material. Material carried forward by the spike lattice is dropped into the weighing pan, which we have seen in the previous diagram, and once the preset amount is dropped, the flap, the closing flap will close and the bottom flap will open. That means, from the previous machine the material is delivered into a weighing pan, and the weighing pan keeps receiving the material, and there is a sensor. When you receive the desired amount of material, suppose we have fixed an amount 1.5 kilo. So, by the time it receives 1.5 kilo, delivery to the weighing pan will stop, and the bottom part of the weighing pan will open, and as a result the material will drop on the conveyor. So, and once the material is dropped, the bottom part will close and the closing flaps at the top will open now, and the material will be delivered to the weighing pan again. So, this is how the weighing pan is going to receive a fixed amount of material always and dropping it on the conveyor. So, same thing will be done by all the blenders. All the blenders one after the other do something. The material from the blenders are dumped on each other and a sandwich blend is formed, which moves into the main line. So, as soon as the conveyor will go from blending feeder 1 to blending feeder 2 position, the material from blending feeder 2 will be dropped on the material which is there already, that is material that has come from blending feeder 1. So, the material from the blenders are dumped on each other and finally, a sandwich blend is formed. So, you see by the time we go to this place, we have a sandwich blend. Here we have a sandwich blend. So, this layer goes here, this layer goes there, this layer goes there, and by the time here we have a small mixture of material coming from 4 different blenders, and then it is going to the main line for further processing. This is how. So, if we want to mix 4 different types of material, we use 4 blenders. If we want to use 3 materials, we use 3 blenders. If we want to mix 2 material, we can use 2 blenders for 1 material, another 2 blenders for another material. So, a lot of possibilities are there if we have a number of blenders with us. Factor affecting blending accuracy, the weighing accuracy of the weighing pans is important. How sensitive is the weighing pan is, what is the tolerance, this is what matters. And the high productions and frequent filling and weighing pan leads to higher CV percentage of the weighing pan filling. That is, if I want to increase the production too much, so the weighing pan gets filled up too fast and dumps the material. So, if the frequency of operation of the weighing pan enhanced beyond a certain limit in order to increase the productivity of the machine, then there is a danger that blending accuracy will suffer. So, you have to know that at what level of production the variation in the weight of the material that is being dumped from a particular blender is minimum. So, we can the different blenders that you use, they can be having, we can set one machine for dumping 2 kilo, another machine for 1.5 kilo, the third machine may be just 800 gram, whatever it is, these things can be set, and accordingly the blenders will work and they will keep dumping the material, forming sandwich blend, and that blend then will go to the main line for further processing. So, this is how the blending is carried out in Prodoom. With this, we close this session and thank you.